Thank you, Dimitri. I'll just share my screen. So thank you. So I'm gonna follow up the remarks that David just provided with a perspective from the data side of the proposal, and as a radio astronomer, perhaps more focused on the drivers from the radio astronomy side as well. So I'm going to be talking about the big data challenges that we face as a BRICS community, driven primarily by the fact that astronomy is changing to a new mode of doing science, consisting of large surveys generating lots of data. So this plot shows a growth of the data sizes generated by large radio astronomy projects in the last 2 decades and forward into the next decade. It's a log linear plot, so the straight lines on these plots represent exponential growth of data sizes. And you see that up to this point in time, there's been an exponential growth with a doubling time of about 2 years, driven primarily by telescopes in North America and Europe. But they're coming up within the BRICS community, we're going to be driving a much faster growth of data, doubling times of about 8 or 9 months, and driven by the facilities that are being commissioned or developed or planned to be developed among the BRICS community. And this represents a new challenge for a community of researchers, and it's a data challenge. A lot of that is driven by our investment and engagement in the Square Kilometre Array. South Africa, China, and India are partners in this project. And we're all engaged in these 3 countries on Pathfinder programs, which lead us to the SKA, and working on addressing the data challenges with the idea of providing solutions for researchers to work with the big data sets that the SKA is going to generate. We're also, many of the BRICS countries are involved in the LSST project, now the Rubin telescope, which is generating similar scales of data challenges in the optical. And these 2 projects are complementary and synergistic. And by working together and bringing the data together, we can generate much more impactful science than alone. This is a summary of data-intensive survey facilities in BRICS countries from the radio perspective. And you see, basically, we all have telescopes that are producing challenges that we're jointly facing in terms of generating large amounts of data that need to be turned into knowledge. So those telescopes are producing big data sets. The other aspect of the challenge is that the sociology of how we do science is changing, driven by this transition to survey programs. So basically, the discipline of astronomy is changing by the fact that we're producing these large, unique international facilities generating big data. Because it's a large community of nations coming together to create a single, very powerful facility. The facility is meant to address a small number of big science questions. And those big science questions are addressed by large programs, these large survey programs. But the users and the people engaged in these projects are not any longer from a single community in a single country, but they're large globally distributed teams. So we have this dynamic of unique facilities generating vast data sets of interest to groups that are distributed all over the world, and in the particular case for this proposal, among our BRICS countries. In South Africa, the Meerkat project, which is a precursor to the SKA, is pathfinding this kind of way of doing science. 65% of the time on Meerkat will be dedicated to 8 large programs, which will be done over 5 years. So each program will be observing the sky for thousands of hours and generating very large data sets. The users of this data are distributed all over the world. And so we're faced with this challenge of big data and distributed teams. What does that data look like? This is an image from a deep radio continuum observation with Meerkat for one of the large survey projects. This is a very small area of the sky. It's about the size of the moon. And everything you see in this image is a radio source. You can really not see the noise in this image. Every object on here is real. And there's tens of thousands of discrete radio objects in this image. And if you expand this kind of imaging project to a large area of the sky, which will be done with instruments like the first phase of the SKA, we can predict that over the next 10 years, several billions of new radio sources will be detected. Those radio sources in themselves represent a big challenge to understand what they're telling us about the universe. But part of gaining that understanding requires us to observe the same pieces of the sky at optical wavelengths. And with the Meerkat projects, we have a complementary optical telescope in South Africa called Meerlik that co-observes the sky with Meerkat to provide an optical image of the same piece of sky and also to detect transient events happening while the observation is taking place. So that we have sort of three data sets to enhance the science. We have the radio survey of the sky, we have the optical photometry from the telescope, and we have the detection of transient phenomenon within those fields. So those three views of the sky combined are a very powerful new way of observing the universe and drive the big data challenge. In the SKA era, well, before the SKA, the LSST is going to be producing data sets similar to Meerlik, but much more powerful over the whole sky. It'll produce photometric image data, and it'll produce transient alerts of millions of objects per night. The photometric data produced by these large surveys are really critical for understanding what we're seeing in the radio, because the spectral energy distribution of the radio sources and the optical tell us two things. They tell us what kind of object we're looking at, whether it's a young galaxy, an old galaxy, an active galactic nucleus. And they also tell us how far away the object is. So we can use the photometric data from multiple colors in the optical infrared to distinguish the kind of object we're looking at and its distance. And then combining that with the radio data, we can understand these sort of the complete history of the cosmic evolution of these objects over time. This challenge then is to take all this data from the radio, from the optical, the large photometric surveys, the radio information, the transient information, and turn that data into knowledge. And that is a new type of problem that the global community is facing with this new era of facilities and projects. This is a slide from the LSST project talking about the challenge of going from data to knowledge. A similar slide can be produced for any project that's on our list. And the problem is to go from the raw data, which is very large, to scientifically useful information, and then to mine that useful information for knowledge and new science. The reason this is not being done currently is because it's a big challenge. There's a computational challenge. We need to bring to bear new technologies and algorithms to make this happen. And there's a sociological challenge that traditionally astronomers have not had the right combination of skills to deal with the kind of data challenges that we're facing. And as you see in this slide, it talks about the fact that we need expertise in statistics, applied math, software engineering, and astronomy, and that requires a new type of person. But things are changing. And the BRICS, the data side of the BRICS collaboration proposal tries to drive that change. So going from data to knowledge, there's sort of four categories of challenges. there's the challenge of globally distributed teams needing to work together on these big data sets. There's the challenge of the data themselves, just the software engineering and the computing engineering. There's the fact that we need to bring together large data sets from many different wavelengths. So the data fusion, how do we jointly work with all this data? How do we convert that data into knowledge? And then there's the ability to work with that data, develop new algorithms involving machine learning and data mining, and to develop the platforms to allow it to work on the big data sets. So these are sort of the four thematic challenges that we want to address within the BRICS collaboration. And we have the collaboration areas that we've identified. Of course, the first one is the science, bringing researchers together on all these facilities to leverage the science. We want to build federated cloud platforms for collaboration and provide the platforms for the processing and analytics. We need to develop new algorithms to explore and analyze the data. And we want to bring those new data science technologies to bear on the development and social benefit challenges that we've identified as well. So that's the challenge in front of us. The data side of the BRICS IDTN builds this data network that brings together the data, the technologies, and the expertise within the BRICS community. We plan to solve the broad technology and data science challenges for the data to knowledge problem. In doing so, we will create collaborations among the BRICS researchers that will basically provide the tools for exploration and discovery. We'll train this new generation of multidisciplinary data scientists that we need to work on these data science and challenges. And we'll hopefully realize the data-driven societal benefits from these new skills and the new capabilities and the opportunities that arise. So that's the end of my presentation.
Thank you, Russ. Questions, please. Actually, I have one. You never mentioned computational statistics. You know that it's quite a big part of science. Maybe it's worthwhile to include this into consideration. I mean,
sorry, I have difficulty hearing you. Could you say that again?
I mean that you never mentioned computational statistics. It's a
computational strategies.
Say again?
You say computational strategies?
Astrophysics. Astrophysics.
Astrophysics. Yes, definitely. It's yeah. The computational astrophysics is at the core of this.
So probably it's worthwhile to include this into consideration because we have a big experience in all countries actually in this field.
Yeah. Indeed. Thank you very much.
Thank you very much, Russ, again for perfect talk. And next talk by Carolina Odman about benefits to society. Carolina, please.